Okay, this video we're going to cover section 8.3 on similarity, and this is going to build off of our lesson from 8.1. So today our goal is that we'll be able to relate similar figures and use the proportionality of known lengths to determine unknowns. So essentially two figures are similar, right? If and only if there's a dilation that maps one onto the other. Or in other words, if I took a figure and I dilated it to a different size, those would be considered similar figures, right? If we change the angles or the proportionality of the sides like we talked about with dilations, then it's a new figure. It's not similar to the original. So corresponding angles, remember, just like we talked about with dilations, they have to be congruent. So the angles cannot change, and corresponding sides have to stay proportional. So if one of them doubles, the other one also has to double. And we can use the scale factor to determine some proportionality there. Remember, we denote that two figures are similar using this symbol, that little like squiggly line. Oh, that's a crazy one. That means similarity. And we can define similarity in similarity statements by identifying what their corresponding angles are. Those are angles that are in the same position in two different polygons. And their corresponding sides, obviously, are the sides between those angles. So if we look at these examples over here on the right, we've got two triangles. We've got triangle ABC and DEF, and we're told down here with this, what we call similarity statement, that triangle ABC, again, there's that squiggle line, is similar to triangle DEF. So when you write a similarity statement, you write the vertices in corresponding order. So by them putting A first in this similarity statement, I know that it corresponds to D. So A should be congruent to D. Those angles should be the same. E is in the middle, and it corresponds, it looks like, to B. And then it says C and F at the end, which means these ones would be the same measure. So the way you write your similarity statement says a lot, or if you're told they're similar, then those angles defined are giving you some information there. So let's just practice with the notation, and then we'll talk about using that scale factor and the proportionality. So first example, in the diagram, triangle IRS is similar to triangle ZXY. So we're told right there. So it looks like IRS, ZXY. I always just look at them to make sure that they're, like, these two are in the same position, right? They look pretty good. So I don't need to kind of reorient it in my mind. Then it wants us to list all pairs of congruent angles, write the ratios of corresponding side lengths, and find that scale factor. And it says find the scale factor from IRS to ZXY. So it's essentially dilating this direction. So I always ask that question like we did with dilation. Is that a reduction or an enlargement? It looks like the shape is getting smaller, so I want to make sure when I get my scale factor that it's less than 1. Find the scale factor from IRS to ZXY. So remember, when we find the scale factor, we take the dilated length and we put it over its corresponding original length. So we look at the dilated image ZXY, and let's say I take 15. That's the dilated length of the side that corresponds to the 25. If I simplify 15 over 25, I end up with 3/5. So that dilated image is 3/5 of the original image. If we want to practice the notation listing all congruent angles, that means, right, if they listed I first, that's congruent to angle Z, or if we look at the diagram, we can see that as well. So the measure, we're not going to write measure because we're not dealing with the actual degree. So let's just write angle I, and we're going to write is congruent to angle Z. So those would be the same. In the same way that angle S, right, would be congruent to angle Y. So we're going to write angle S is congruent to angle Y. And then the last one, angle R, would be congruent to angle X. So those are congruent statements. Then if we move to proportionality of the side lengths instead of angles, we're going to write a statement of proportionality. So you're just saying which side lengths correspond to which side lengths, and we want to make sure we go the same direction every time. So if I want to start with ZX, that corresponds to IR, right? Then ZY is going to correspond to IS. So each of these will just correspond. So let's say, again, I start with ZX, that corresponds to IR. ZY corresponds to IS. and XY, the bottom of that triangle, corresponds to RS. So that's what we call a statement of proportionality. Again, notice that my triangle ZXY, all of those ones are on the top and the IRS is all on the bottom. So if we were to actually write the numerical values in here, those would all end up being the same fraction, actually this fraction of 3/5. Okay, there's another one if you want to practice it, but essentially that's the same thing. So turning over to the back, using this scale factor then, or finding the scale factor given an image, and then using that scale factor to help us find missing pieces. So this says the polygon in each pair is similar. So we're told they're similar. We can assume that. If the polygon on the left is dilated to create the polygon on the right, so we're being told that this was dilated this direction. So that smaller image became larger, right? We know it's an enlargement. State the scale factor, then find the missing side. So let's start with the scale factor. And remember we talked about on that last page, the scale factor, we take one side from the dilated image, so 48, and we divide it by its corresponding side in the original image. So 48 over 40, if we divide each of those by 8, we end up with 6/5. So this image is 6/5 the size of the original one, right? It's a little bit bigger because 6 over 5 is more than 1. Then we can use the scale factor essentially to multiply or divide. I'm going to use proportions just because we'll practice them for our trig unit. So if I want to find the missing side, I'm going to say, well, 48 is to 40, or this proportion should be the same as 18 is to that missing side, right? Because 18 is in the same position as the missing side on the larger polygon. Once we have a proportion set up, this is where we cross multiply. So I don't know if you remember doing this in the past, but we do 40 times 18. That gives me 720. Then I cross multiply the other diagonals, which I end up with 48x. We then divide by 48, divide by 48, and I believe x comes out as 15. Okay, so that missing side length would be 15. Now you'll notice up here on the shapes, 15 turned into 18, right? It grew by 3. 40 turned into 48. It grew by 8, right? When you use proportionality, it's not that we're adding the same thing every time. It's growing by 6/5, and 6/5 of 15 is smaller than 6/5 of 40. So when we use these proportion statements, it just helps us take care of that. Okay, let's do another one. So scale factor here. Again, just to practice, we take a side on the dilated image, and they told us we're headed this direction, left to right. So we're going to take 20 and put it over 24. If we divide each of those by 5, we end up with, let's divide them by 4. 5 over 6, if we divide them by 4, so 5/6, which makes sense. Again, we want to make sure that it makes sense because this image is getting smaller, so 5/6 is less than 1. Then I set up my proportions. So 20 was to 24 as 30 is to the missing side. So 30 is to x. Then we cross multiply. So 30 times 24 is again 720. And 20 times x is 20x. Divide by 20. And x is going to be 36. Then again, we just make sure that it makes sense, right? This was a bigger image. 36 turning into 30 would make sense. Okay, I'm just going to do that many. But if you look at C, you could tell this one without doing any actual like fractional calculation. This image, moving to this image, is definitely getting smaller. And if 10 turns into 5, hopefully we can tell that the scale factor on this one would be equal to 1/2. It's getting half the size. So if I want to determine x, right, 12 turns into x, I'm just taking half of that. So x would be equal to 6. Very good. Okay, the last two kind of ideas from this one is we can correspond each of the sides of similar polygons, but we can also correspond their perimeters and their areas. Now their perimeters, because it's just the sum of the distance of all the sides, when we correspond like 10 is to 15 in the same way as x is to 18, we could find x. And then we could do it again and do 10 is to 15 as this is to 9, and we could try and find all the sides. But this says that the two gazebos are similar, and we want to find the perimeter of gazebo A. So I don't really need all the side lengths unless I have them to add up. But what we can do, because their sides are proportional, their perimeters, which are just the sum of the sides, are also proportional. So if I know the perimeter of polygon 1 and I just put it over the perimeter of polygon 2, that's the same thing as, or the same ratio, if I took the side length of polygon 1, or one of the side lengths, and put it over its corresponding side length of polygon 2. Okay, so let me show you what that means. So again, if I take perimeter of polygon 1, well, if I jump down here, my goal is to find the perimeter of gazebo A. I don't know what it is. So that's my kind of my unknown. I'm going to put P over the perimeter of polygon 2. I can add this up. That's going to be 15 plus 18 plus 15 plus 12 plus 9 is 69. So it's 69 meters over here. So P is to 69 perimeter, as 10, one of his side lengths, would be to one of the other side lengths that corresponds. Now again, we just have a proportion to simplify, so 690 is equal to 15p. We divide by 15, and I believe we end up with 46. So in this case, that perimeter would be 46 meters. Okay. Right below that, it says two polygons are similar. The ratio of the corresponding side lengths are 3 to 4. So instead of giving you a picture, it gives you the ratio there. So that's like saying 3 is to 4, just like we said, like 10 is to 15. And then it says the perimeter of the larger polygon is 56 centimeters. So when I set up this ratio, if 56 is the larger polygon, then 4 must be coming from the larger polygon, so we'd put 56 on the bottom of this fraction, and then we're finding, oh, I was going to draw a P, but that looked weird, the perimeter there. So we know that 3 is to 4, as the perimeter of the smaller one would be to the perimeter of the larger one, and then we can go ahead and solve. So we get 4P is equal to, we multiply 3 times 56, which is 168. Then we divide that by 4, and we end up with P is equal to 42 centimeters. Okay. Area is very similar as far as setting up the ratios. However, area, because we're in squared units, relates just a little bit different. So the area of polygon 1 over the area of polygon 2 is, just like the last one, a side length. We use a side length of polygon 1. But we need to use the square of the side length because we're dealing with area. And then we take that corresponding side length, pretend that says length, of part 2, and we use the square of that as well. So the areas are related to the squares of the corresponding sides. So jumping down, let's try this example. This says, in the diagram, GHJK is similar to LMNP. Find the area of LMNP, so we don't know the area of this figure on the right, if the area of GHJK is 84 meters squared. So I'm going to write it in there so I know that belongs to that one. So again, if I'm using this property up here, I would just say, okay, well, I don't know all the other side lengths, but I do know that 84 is to the unknown area as 7, because it comes from the polygon with an area of 84, is to 21. But again, we want to use the squares of those values because it's area. Then we go ahead and simplify. So we have 7 squared is 49 times A. So this is 49A. 21 squared, if we multiply that, right, by itself, we get 441. And times that by 84, we get 37,044. Divide by 49, and A would be equal to 756 meters squared. So remember, this is area. And again, I would just check to make sure it makes sense, right? If this is 84 and it's growing, then that area should be significantly larger, which it looks like it is. Okay, that's essentially the end of this one. I'm going to do one more example, but it's just the same thing. So again, we just look down here. It says in the diagram, triangle ABC is similar to triangle DEF. Find the area, so again, making sure we understand area of DEF if the area of ABC is 36 centimeters squared. So ABC, I'm going to write 36 squared centimeters in there. And again, we set up the ratio. So 36 is to the unknown area in the same way as the square of its side should be to the square of the unknown area's side. So we then cross multiply, so 10 squared is 100 times A. 36 times 5 squared. 5 squared is 25. So if we multiply 25 by 36, we get 900. So if you divide by 100, the area of that smaller polygon would be 9 square centimeters. Okay. So the biggest thing on that one is recognize, are you doing perimeter or are you doing area? And that's really the difference between if we need to use the squares of the sides or just the corresponding side lengths themselves.